Hi there. So picking back up from where we left off, a solution of a differential equation is a function that makes the differential equation true for all x's in some interval. So if you look at the second order linear differential equation, which of the following is a solution? Okay, we have A, the sine of 3x, B, the sine of 2x, and C, the 5 times the cosine of 3x. Let's take a look. So, looking at A, y equals the sine of 3x. According to our differential equation, we need y double prime plus 9y to be 0. So I need y prime, which is 3 cosine 3x, and y double prime, which is minus 9 sine 3x. Okay? And I'm going to take these bits of information, I'm going to plug them in. So I'll plug there into y double prime and this in for y, and we'll see if we have a true statement. So y double prime is minus 9 sine 3x plus 9 times in brackets. Let's see, sine 3x. So the question that we ask is the left-hand side equal to the right-hand side for some interval of x's? In other words, is 0 equal to 0 for some interval of x's? And of course that is. It's true for all x's. So this is a solution. How about B? Okay, the sine of 2x. So if we do the sine of 2x, run through this real quick. Y prime is 2 cosine 2x. Y double prime is minus 4 times the sine of 2x. And let's see, y double prime. So if plugging these bits of information into our original differential equation, y double prime plus 9y equals 0. What do we get? Well, minus 4 times the sine of 2x plus 9 times, in bracket, what y is, the sine of 2x. So we get minus 4 sine 2x plus 9 sine 2x, that's 5 sine 2x. And that is equal to 0 for some x's, but not an interval of x's. Okay, so like x equals 0 and pi and 2 pi and all of that makes this true, but not an interval of x's. So you can't say that this is true for x's between negative pi over 2 or positive pi over 2, something along those lines. So because that's not the case, this is not a solution to the differential equation. What about part C? Y equals 5 times the cosine of 3x. Go through the process one more time. What's 5 times 15? Minus 15 sine 3x. Multiply that again. We get minus 45 times the cosine of 3x. And we're plugging it into y double prime plus 9y is 0. So that's minus 45 times the cosine of 3x plus 9 times whatever y is. What is y? It's 5 cosine 3x. And minus 45 plus 45, we get 0 equals 0. So that is a solution. So what we have here is two solutions to this second order linear homogeneous differential equation. As an afterthought, you might be thinking, well, this had an argument of 3x, this had an argument of 2x, this has an argument of 3x, and the ones that had an argument of 3x were both solutions. So what would happen if you looked at the equation y equals 5 times the cosine of alpha of x, where alpha is not equal to 3. Is this a solution? Okay, well, let's kind of do that. D, even though there's not a D there, y equals, what, 5? Yeah, 5 times the cosine of alpha x. So alpha is some parameter here. That's 5 alpha sine alpha x, and I know I'm missing my parenthesis, or my negative. Y double prime is minus 5 alpha squared cosine alpha x. Plugging that into y double prime plus 9y, do we get that equal to 0? So minus 5 alpha squared cosine alpha x plus 9 times whatever y is, that's 5 cosine alpha x. Is that equal to 0? Big question mark. So you see both these have a cosine alpha x in common, so we can factor that out. Both of them have a 5 in common. We can factor that out. What am I left with? Minus alpha squared plus 9 is equal to 0. Okay, is this true for some interval of x's? Well, we know that there's no interval of x's that will make this equal to 0. So the only question is, what values of alpha will make this equal to 0? So minus alpha squared plus 9 is equal to 0 means 9 equals alpha squared, which means alpha is plus or minus 3. So the only solution to this differential equation is going, that's of the form 5 cosine alpha x, is the ones where alpha is either a positive 3 or a negative 3. Okay? And if you look at the cosine function, it's symmetric about the y-axis. And so whether it's a cosine 3x or cosine negative 3x, the graphs are going to be identical, so it really doesn't matter whether it's a plus 3x or a minus 3x. Now, the follow-up is what happens if this were to be different? Instead of 5, let's say it's 15 or 45 or something like that. Well, the answer is our next theorem. For any linear homogeneous differential equation, if y equals f of x is a solution, then so is y equals that any arbitrary constant times f of x. So that means, in the example that we just did, not only is sine 3x a solution, but so is 2 sine 3x, and 3 sine 3x, and 5 sine 3x. And the same thing here, 15 cosine 3x is a solution. 45 cosine 3x is a solution. So that's a nice little theorem to keep in mind as we go forward. A bit of vocab, the general solution to a differential equation represents all possible solutions at once. A particular solution is just one function that solves a differential equation. So we know from our work that we've just done that sine 3x and cosine 3x are each particular solutions. Okay? We also know that, more generally speaking, that A, doesn't matter if it's A is 1, 2, 3, 5, and B, I'll call this, instead of 5 cosine 3x. So anything of the form A sine 3x and B cosine 3x are also solutions to that differential equation by virtue of the theorem that I just stated. Therefore, a general solution, it's not hard to show, we won't show it, but it's not hard to, says that any function that's of the form a cosine 3x plus b sine 3x is the general solution to this differential equation. Okay, in this case, this particular solution, a is equal to 1 and b is equal to 0. In this case, y equals 5 cosine 3x, b is equal to 5, a would be equal to, a would be equal to 5 and b would be equal to 0. I have them backwards, or I said them backwards. Okay, so things that you want to keep in mind from this page is definitely this theorem. Okay, this is a good one to know. How to check whether a function is or is not a solution to a differential equation. That's going to be important. And what's the difference between a general solution and a particular solution? Okay, so these are all important pieces on this page. This is probably one of the more important pages of this lesson. All right, so for the last one. For any linear homogeneous differential equation, the general solution has exactly as many arbitrary constants as the order of the differential equation. So keep that in mind. We just looked at the differential equation y double prime plus 9y equals 0. And the order of this differential equation is 2. So that means there are 2 arbitrary constants in the general solution. Remember what the general solution was? A times cosine 3x plus b times the sine of 3x. Arbitrary constant 1, arbitrary constant 2. Okay, so our example does not violate this theorem. It actually supports it. Now, I know that some of you might be kind of yelling and screaming at the video, hey, what did you talk about alpha being plus or minus? Okay, what about the minus 3x? I just want you to draw it to your attention that cosine 3x is the same as the cosine of minus 3x. I already established that or alluded to it in the image above. But the sine of negative 3x is equal to negative the sine of positive 3x. Okay, and that's just part of that arbitrary constant out in front. So even though we're talking about cosine 3x and sine 3x, we could as easily been talking about the cosine of negative 3x and the sine of negative 3x, and they are still a part of this general solution. They're reflected in that. Okay, down the home stretch. An initial value problem is a differential equation and some extra conditions. Call them initial conditions. You need a particular solution to satisfy. Okay, so example 4 here says y double prime plus 16y equals 0. We want to find the particular solution to this differential equation that satisfies the condition that y of 0 is 3 and y prime of 0 is 5. So first we're going to find the general solution to the differential equation, and then once we find the general solution, we're going to solve for the arbitrary constants that make the initial conditions true. Okay, so in light of the example that we just did for y double prime plus 9y equals 0, providing a general solution of this, I'm going to claim, and we'll prove our claim, that y equals a cosine 4x plus b sine 4x is the general solution to y double prime plus 16y equals 0. So we'll start off there, okay? And once we demonstrate that to be true, we can find the particular solution that has this as its y-intercept and this as the slope of the line tangent to the graph at x equals 0. All right, let's go. So if this is y, then what is y prime? Y prime is minus 4a sine 4x plus 4b cosine 4x. And what's y double prime? Minus 16a cosine 4x minus 16b sine 4x. So we have y double prime here, we have y here. We can substitute into this differential equation. Let's see what we get. Minus 16a cosine 4x minus 16b sine 4x plus 16 times whatever I'm claiming y is equal to 0. What is y? It's a cosine 4x plus b sine 4x. Let's distribute this 16. We get 16a cosine 4x. You get 16b sine 4x. That's equal to 0. What do we have on the left-hand side of the equation? Minus 16a cosine 4x and minus 16b sine 4x. And so the positive and negatives cancel each other out. You're left with 0 equals 0. So my claim was true that this is the general solution. Now, we have two initial conditions. One is that the y-intercept is 3. Y of 0 is 3. And the slope at 0 is 5. So, let's see. Using this first, okay, I can plug 3 in for y and say that 3 is a times the cosine of 4 times 0 plus b times the sine of 4 times 0, because after all, x is 0 in this case. This is the sine of 0. The sine of 0 is 0, so b times 0 is 0, and I'm left with 3 equals a times the cosine of 0, which is 1. So a is equal to 3. Perfect. Go back up here. That is 3. So now I use my information about y prime of 0 is 5. So if I were to go to my work above, y prime is equal to 5 equals minus 4 times, we just saw that a is 3, times the sine of 4 times 0 plus 4 times b times the cosine of 4 times 0. Just plugging in what I know for a, what I know for x, and what I know for y prime. What does that end up being? Running out of space up there. Probably didn't have space to begin with. 5 equals minus 12 times 0, 0, plus 4b times the cosine of 0. Well, we said the cosine of 0 is 1, so 5 is equal to 4b, so b is equal to 5/4. We have our particular solution. Okay, so y is equal to 3 times the cosine of 4x, because 3 was a, and b is 5/4, so it's plus 5/4 times the sine of 4x. There you go. All right. So show that C1 cosine 4x and C2 sine 4x is a solution to the differential equation. We actually have already done that. Find the constants that solve the initial value problem. We just did that. Okay, last one. Y triple prime equals 6x. Y of 0 is 1, y prime of 0 is -1, y double prime of 0 is 4. Well, what's different about this differential equation that the others, from all the others that we looked at? Well, this differential equation, y triple prime equals 6x, involves x and not y. Does this remind you of anything? It should. Okay. This is a simple integration problem. So, look at this. If y triple prime equals 6x, okay, then y double prime is 3x squared plus a constant, call it C1. What's y prime? Well, that's equal to x cubed plus C1x plus a constant, call the second constant C2. And what's y? Well, that's x to the fourth over 4 plus C1x squared over 2 plus C2x plus a third constant, C3. Okay, and that would be the general solution to our differential equation. Okay, what is the order of this differential equation? The order of this differential equation is 3. How many arbitrary constants do we have? 1, 2, and 3. Not a coincidence. Okay. We have 3 initial conditions. Y of 0 is 1. So we can play that one out. 1 is equal to x to the fourth, well, 0 to the fourth over 4 plus C1 times 0 squared over 2 plus C2 times 0 plus C3. Well, looks like C3 is equal to 1. Okay, so I'll put a 1 right there. Next, y prime of 0 is negative 1. So if I look at the y prime equation and say negative 1 is equal to 0 cubed plus C1 times 0 plus C2. So that means C2 is equal to negative 1. I'll put a negative 1 right there. And lastly, we know that y double prime of 0 is 4. So let's kind of separate these out. Boom, boom. Y double prime of 0 is 4. So 4 is equal to 3 times 0 squared plus C1. So C1 is 4. Put a 4 right there. And our particular solution is going to be y equals x to the fourth over 4 plus 4 over 2, that's 2x squared minus x plus 1. So this is the only function that will solve this differential equation and satisfy these initial conditions. Okay, no other function will, only the one that I'm pointing at right there. All right, so hopefully this gives you enough to get started from section 1.2. Okay, I'll have another video for you tomorrow with section 1.3.